Once again, welcome to our channel. In last class, we discussed about the parameters of transmission line. In parameters of transmission line, we discussed about the resistance, the effect of inductance, and the effect of capacitance. And apart from that, we also discussed about the different types of transmission systems that are available in electrical energy to be transmitted from one end to the other end. And today we are here to discuss about the significance of end condenser method that is available in medium transmission lines. So in medium transmission lines, we also discussed about different types of medium transmission lines. One is end condenser method. Already the same is discussed. First one is end condenser method, and second one is nominal T method, and third one is nominal pi method. So today we are here to discuss about the ABCD parameters that are available for end condenser method. So I am here to discuss about the end condenser method, and the diagram is shown for the end condenser method. This is the resistance that is available for the transmission line network, and this is the inductance R, XL, and basically it is our load which is consisting of RL load, and this is our receiving end voltage, and at this location we are supposed to connect the capacitance. So the name again itself is self-explanatory that the capacitance is connected at the receiving end. That is why it is called as end condenser method. And this is my sending end voltage that is represented here, and this is my sending end current, and this is my load current or receiving end current IR, and finally this is my capacitor current. So this is written as load. So as I said earlier, it consists of RL load, and a capacitance is connected across the receiving end. So if I want to represent, so this is a diagram which represents the end condenser method. And one more thing which I would like to mention here is that the phasor diagram that represents the end condenser method. This is my VR that is supposed to be taken on the x-axis with an angle of 0 degrees, or it can also be represented as VR plus J0. And either we can draw the IR that is supposed to be drawn from this location or from this location. Okay. So it is easy for us to draw IR from this location. This is my IR, and at this location we are supposed to draw the capacitor current IC, which is supposed to be taken at an angle of 90 degrees, and the angle that is available from here to here is 90 degrees. At the tip of IC, I need to join the 2 points to find the value for IS. So this is my IS, whereas this is my IC, the angle that is available. Okay, and this is my IR, and this is my IRR, and this is my IRXL, and when you add, this is my IRZ, and when you add the two things, where VR with your VR with respect to my, so this is called as my VS, and see here, so this represents the phasor diagram. So it is drawn with OA is drawn with angle of 0 degrees. It is taken as the reference axis, reference value VR, and it is supposed to be defined as vector VR is equal to VR plus J0. VR plus J0, and this is my IRR and this is my IRXL. When I add the two things, this dotted line represents the IRZ. So when VR it is added with the, so that you can obtain the value for your Vs, and you can see here this is my theta 1 and you can also consider as your theta 2. The angle that is existing between Vs and Is is taken as theta, that is taken as theta 1 plus theta 2. So theta 1 plus theta 2 is with the angle that is available between Vs and Is. And today we are here to discuss about the ABCD parameters that are available for end condenser method. So apart from that, we are here to frame certain equations related to end condenser method. So IR is defined as, IR can be written as IR at an angle of cos pi r minus j sin pi r. See here, IR is the current that is taken by my load, receiving end current. So IR can be calculated in such a way that IR is defined as, IR is equal to the power drawn from the secondary end, receiving end, P divided by, it is root 3 VL cos pi, where cos pi is the power factor of the load and P is the power that is drawn by the load, and root 3 VL cos pi defines the value for IR. So IR is obtained in polar form having certain magnitude. So I need to resolve this IR into two components. One is IR cos pi r and second part is my minus j sin pi r, because since I am using the inductive load, the current IR has to be resolved into two components. One is called as IR cos pi r and second part is my minus j sin pi r, minus j IR sin pi r. And with this IR, once if it is calculated, okay, and next fact is that we need to calculate the current that is passing through the capacitance. So IC can be defined as VR divided by minus JXC. See here, the capacitance is connected across the receiving end. Once the capacitance, if it is connected across the receiving end, so it can be defined as VR divided by minus JXC. So it can be defined in such a way that VR JVR into, it is defined as omega C. JVR divided by XC, XC is equal to 1 by omega C. So it becomes JVR into omega C. Omega, you might be knowing, omega is equal to 2 pi f. And we need to add the two things to obtain the value for IS. So IS is equal to here IR plus J VR omega C. So IR can be written as IR of cos pi r minus J IR sin pi r plus J VR into omega C. So the entire value stands for the value for your IS. And finally, when you want to calculate the value for Vs, sending end voltage Vs, so Vs is equal to VR plus Is into Z. So after calculating the value for Is, okay, the value for the Vs can be obtained in such a way that Vs is equal to VR plus Is into Z. So this can be defined in such a way that, okay, so Vs is written as VR plus Is into Z, whereas Is is defined as IR cos pi r minus J IR sin pi r minus J VR omega C. So J omega C can be taken as J, for your reference purpose, J omega C can be taken as Y. Okay, Y is called as my admittance. Truly speaking, it must be susceptance. Okay, but admittance is equal to your conductance plus or minus susceptance value. So J into omega C will be your Y. So, and one more thing, so from these equations I need to frame the values related to the ABCD parameters, and we will solve it right now. So in end condenser method, Vs is defined as Vr plus Is into Z, where Is is the sending end current that is available from the sending end, and Vr is equal to Vs is equal to Vr plus Is into Z, where Vr is my receiving end voltage. So the same is written here, Vr plus Is can be written as IR plus IC. IR plus IC can be taken as my Is. So IR plus IC into impedance Z. So it can be written in such a manner that VR plus IR can be IR into Z plus IC into Z. But the fact is that IC is the capacitive current that is available at the receiving end. So this particular current, capacitive current, is obtained through the voltage that is available at the receiving end. So it is defined as Y into VR into Z, because Y is defined as Y is equal to J into omega C. Already we discussed about Y is quite equal to J into omega C. Okay, so it is defined as, okay, that is Y is defined as here J into omega C. So thereby IC can be written as here Y into VR. IC can be written as Y into VR. Okay, so Y into VR, that is multiplied by the impedance Z. So if VR is taken as a common factor in these two cases, it becomes VR into 1 plus YZ, Y into Z, YZ plus IR into Z. This is the equation which defines for the Vs value. And on similar lines, okay, Is can be defined as IR plus IC, but IR can be written as such IR plus IC can be written as here Y into VR. So Y into VR. So obviously it becomes in such a way that, okay, Y into VR, and it can be written as VR into Y. Sorry, it is a mistake here. So Y into VR plus IR. Okay, so it is if you want to mention in terms of here VR, so VR multiplied by Y plus IR into 1. Okay, if I want to mention in terms of a matrix here, so Vs can be written as 1 plus YZ, that is available with Z. Z is available from here, that is IR into Z, and Is can be written as here, Is can be written as here VR in terms of here Y, okay, and IR can be, the quotient for IR is 1 into IR is 1. Okay, so and see here, so if I want to define for a transmission line, either for this symmetrical or reciprocal, okay, for symmetrical case, the value of A should be identical equal to the value for the D. If the value of A, if it is identical, because this is defined for the matrix A, B, C, D. Okay, so this is defined for the matrix A, B, C, D. A is defined as 1 plus YZ, and B is defined as Z, and C is defined as Y, and D is equal to 1. Okay, this is defined as in the form of a matrix. So if it is defined in terms of a matrix, okay, so if A value, if it is quite equal to D, the transmission line network should be the symmetrical. Okay, and on similar lines, if A is not equal to D, then in such cases the symmetrical transmission line will not be a symmetrical transmission line. Okay, so and if I want to say for the reciprocal, okay, reciprocal in the sense, what exactly is reciprocal? If the sending end voltages, okay, if they are interchanged, okay, the ratio of the voltage source to the response should remain always constant. Okay, when we are sending source voltage as Vs from the sending end, and then on the receiving end side we are calculating the value for IR. If the ratio of Vs by IR or VR by Is, if the ratio stands the same value, then the transmission line could be the could always be a reciprocal one. Okay, if it could be a symmetrical, the value of A should be identically equal to D. From this, okay, I would like to mention here is that the value of A is not identically equal to the value of your for your D. So these two values are quite different in such a way that here the values are quite different. Okay, in other words, I can say that this particular transmission line is not a symmetrical transmission line. Instead, it can be unsymmetrical, that the value of A is not equal to D. In other words, I can say that this is an unsymmetrical transmission line network. Rest of the things we will see it by next class regarding the nominal T method and nominal pi methods. If you had any doubts, keep it in chat box.